This is a video related to Riemann sums in a Calculus 2 problem. This is a practice example for moving to Riemann sums for Calculus 3. So what we're considering here is a function f of x, and we are trying to find the area under this curve where we're looking over some sort of interval. So we are considering, some function f of x, right? And, we're looking at some interval, possibly this interval could be a to b, the interval I could be a to b, okay? And by doing this integral, you would find the area under this function on this given interval, and that's what this number would represent, this volume, this area, I'm sorry. So as a special case, can we just consider the function f of x is equal to x, and let's consider the interval I to be 0, 1. Okay, and so the idea of this example is not to find the volume, because if you were tasked with that, you would probably just do the fundamental theorem of calculus, x squared over 2 from 0 to 1, and then you would get the area of a half. Okay? But the point of this example is to do the Riemann sum approach. Okay? And you'll remember that the Riemann sum approach takes this function, f of x is equal to x, and we're looking at the interval from 0 to 1. And the idea here is to break this function up into subintervals, this interval I up into subintervals. Let's say you just go up to a half. So if you choose n is equal to 2 subintervals, right? Then you would have the interval 0 to a half, and then you would have the interval from 1/2 up to 1. And then your choice is to choose left endpoints, left, right, or even midpoints. Okay? So in this case, let's just choose the right endpoints. You have a choice. We're going to choose the right endpoint problem. And so you evaluate your function at the right endpoints. Right? And here you have the area of those rectangles. So the Riemann sum approach is to say that the area of this function f on the interval I is approximated by the function evaluated at a half times 1/2 plus the function evaluated at 1 times 1/2. So clearly this number gives you the height of the box, and this number gives you the width of the box. And when you put these two together, these two numbers together, you have the height of the box times the width of the box, and you're getting the area. Right? So clearly you compute this function. The function evaluated at a half is just a half. The width is a half, so that the area of this first box has an area of 1/4. The area of the second box has a height of 1 and it has a width of a half. And so what does that give you? 1/4 plus 1/2, and whatever that comes out to be, 3/4. Why is that true? 2/4, 3/4. What did I do? The interval 0? Oh, so remember, I'm sorry, I paused here because I was looking at this number and I was comparing it to this number, and I was saying those aren't equal, right? And they're not supposed to be equal because you're only getting approximation. The 1/2 is the exact answer, and 3/4 is the approximate answer. So this is your approximate answer, and this is your exact answer. All right, So the question is, how do we do the Riemann sum problem? Okay. And here we have chosen in this problem two subintervals. So you'll remember that the function from Calculus 2, you should remember that the function, if you want to find the area under the function f on the interval I, that will be equal to, and I'm going to put this in quotes, but the limit as the number of boxes or subintervals goes to infinity. The limit, okay, so we're going to take an infinite number of boxes and limit number, and we are going to choose, we're going to sum the area of the boxes. Okay, and we want to sum the area of the boxes as the number of boxes goes to infinity, right? So that has a name. We can write that down a little more formally. I could write that as the limit as n goes to infinity, okay? And I could write the summation is equal to 1 to n of the function evaluated at, in this case, 1 over n times 1 over n. So in this case, our n was 2, so we were evaluating the function at, oh, sorry, this should be an I. Okay. So notice that this formula right here reduces to the above example, reduces to above when n is equal to 2. So for example, this little piece right here will reduce to the formula above. So if you just do summation I equals 1 to 2, fi over n times 1 over n, and you let I is equal to 1, you will get the function evaluated at 1/2 times 1/2 plus, and when I goes to 2, 2 divided by 2 is 1, so you'll get the function evaluated 2 divided by 2, and then times 1/2. The width of the rectangles is not changing, it is always 1 over n, where n is whatever number you choose. The higher the n, the narrower the box is. Okay. So we just need to approach this limit problem. Okay. The way to tackle that problem is in two steps. We want to first compute the summation. Okay. And you're looking for, when you compute this summation, at the end of this step, it should have a formula with n's in it. That is how you know you're finished. You have a formula with all n's in it. The second step then would be to then compute your limit. Okay. So let's go through that process now. We're going to first compute this, evaluate this summation, and then we are going to compute the limit. And if we can do both of these steps, we should get the exact area under the curve using the Riemann sum method. So these two steps are the Riemann sum. Okay. So let's move on. We wanted to compute the limit as n goes to infinity. That is the second step of the summation I equals 1 to n, where n is the sum number of rectangles. Let's leave it unevaluated. Let's leave it. Okay. I goes from 1 to n. This is the height of my rectangle, and then I'm going to multiply by the width of my rectangle, which is 1 over n. Okay. Because the function f in this example is the function f of x is equal to x, this is going to imply that the function evaluated at I over n, whatever you put into this function, you get the same thing out. So you will get I divided by n times 1 divided by n, that is the width of your rectangle, And we now need to kind of work with this summation just a little bit. It reduces to the summation I equals 1 to n, I divided by n squared. Okay. Well, I'm still not to the limit, so I have to keep carrying this around. The thing to notice here is that this is a summation on I, so according to the summation, I is the variable. That means n is a constant. So I can bring the n squared out in front of the summation. And I have in here, I have to add up the numbers I equals 1 to n of I. So just to give you an example of what I'm talking about here, I equals 1 to n of I. Right? If, for example, n had been 4, then what we were trying to talk about here is when I is 1, you get 1. The summation says when I goes to 2, you have to put a plus, add it to 2, add it to 3, add it to 4. And if you were to sit down and add these numbers up, you would get 7, 9, and 10. Okay? But there's an interesting formula that this is the same thing as n times n plus 1 divided by 2, when in this case we went to n is equal to 4. So if you use this formula with n is equal to 4, you will get 5 times 4 is 20 divided by 2, which is 10, okay? Which is the same answer. So what I've just indicated here, this is a summation that you should probably know and write down. I equals 1 to n of I. If you add up the numbers 1, 2, 3, 4, 5, 6 up to n, that will sum up to n times n plus 1 divided by 2. And we can use this formula to replace this summation with a formula that has a bunch of n's in it. So you now bring this limit down, take the limit as n goes to infinity, 1 over n squared, and that big summation we replaced with n times n plus 1 divided by 2. Okay. And now we have a limit that we can try to take. We are at the second step now. Maybe I can simplify this a little bit. This will be n squared plus n divided by 2n, right? Oh, sorry, that's 2n squared. And if you try to look at this limit, maybe L'Hopital's rule is in order, or I prefer just to simplify a little bit, do some algebra. This is n squared divided by 2n squared. If you do the algebra correctly, n divided by 2n squared. Okay. This reduces to a half, and this reduces to 1 over 2n. So you're now looking at a limit as n goes to infinity of 1/2 plus 1 over 2n. And properties of the limit says that you can take the limit of the two terms separately. The limit of 1/2 is 1/2. And as n goes to infinity, this piece is going to go to 0. So the Riemann sum, we get a half here. So if you were to compute the limit as n goes to infinity, take the number of boxes going to infinity of adding up all the boxes, but you're going to add up n of them. You're going to have the height of the box, okay? And then you will have the width of the box is 1 over n. We have just showed that that limit is a half, which is exactly what you would get by doing the integral from 0 to 1 of x dx. Okay? So this is how you would start doing, this is how in Calculus 2, or Calc 1 and Calc 2, you started doing integration. We started by doing the Riemann sum. Okay? And you can then make the definition that if you had the integral of a function f of x dx of a to b, so the interval I here is the interval x interval a to b, that this would be the limit as n goes to infinity, and this would be a definition. If you wanted to know what this symbol, the integral symbol, meant, it would be the limit as n goes to infinity of, and you would have to compute your boxes. I is equal to 1 to n. And one example would be to do the function f of a plus I over n. And then the width of each of the boxes is 1 over n. So this particular formulation is this particular formulation would be using right endpoints. Right endpoints. How do I know that? I know that because if my interval was A to B, right? And you break this up into subintervals, okay? What I mean by that is break them up into intervals of 1 over n. So if I go here to 1 over n step away, this would be A plus 1. Oh, sorry, B minus A over n. I should put a B minus A over n. And this should be an I times B minus A over n. So if you go B minus A over n, that's your little step size. And then if you do that n times, right? So when I is 1, you get A plus B minus A over n. That would be just this little piece. And if you do that n times, you would get A plus B minus A divided by n. And you would step over n times. You would get A plus B minus A, which would be B, which is your endpoint here. So the fact that I'm using this particular form is the right endpoints formulation. And that is one formulation for the limit equaling this, this integral here. Okay. So I think this is an example you should be able to follow through. The key idea was to remember that when you're computing your summation, this was a very key formula here. This is the key to this problem because your first step is to try to compute this summation and to get it down into a formulas that have only n's in it. So you would like to remove all of your I, you want to get rid of the summation and replace it with a formula that has only n's in it. And this is the key on this problem, and for a nice linear function, this is the only summation you'll need to remember. Okay? So the trick is going to be extending this idea to double integrals, which means that we're going to have a function of two variables, f of x and y, and then instead of one integral, we'd have to do two to find the volume under the function. So that is the subject of the next video.